having discussed the thermodynamics of classical harmonic oscillators using canonical ensemble, now it's our turn to discuss the quantum harmonic oscillators in the same ensemble formalism. Okay, so the difference between a classical treatment and a quantum treatment of harmonic oscillators is that their energies, expressions for their energies are different, right? In the case of a classical, like maybe the harmonic oscillator or any other system, the energies vary continuously. That is why we have taken, while discussing the classical picture, the energy of the harmonic oscillator was taken as the sum of the kinetic energy p square by 2m and that of the potential energy, that is half m omega square q square, where the q and p can vary from minus infinity to plus infinity. Theoretically means there is a continuous variation of these quantities that was permitted there. Now, unlike that case, in the case of quantum harmonic oscillators, the energies are quantized. Okay, so what we are going to do here is that we are going to consider a system of n localized. Once again, we are treating that these harmonic oscillators are localized, like in the lattice sites, non-interacting. We consider that they are non-interacting, means each of their energies or energy of each of the harmonic oscillator in the system is independent of other. So non-interacting, quantum, non-interacting quantum one-dimensional harmonic oscillator. That is only for simplifying our mathematics. One-dimensional harmonic oscillators, and in our quantum picture, what is relevant is angular frequency omega frequency omega at a temperature T. We are supposed to specify the temperature for all systems discussed under canonical ensemble, right? Okay, now their energy eigenvalues. So from our previous knowledge, the energy eigenvalues, better we'll use the quantum terminology. Energy eigenvalues are given by what are the energy eigenvalues? That is En. Okay, energy of the nth state, that is equal to, it is given by n plus half h cross omega, or n plus half h nu, whatever you, in terms of nu, but omega is a preferred quantity. So where, what are the value for n? From your vibrational quantum theory or from vibrational spectroscopy also, you are familiar with this particular equation. This gives the energy of the vibrational levels. Okay, where we consider the things to be harmonic oscillator type. So 0, 1, 2, 3, and so on. So let me call this energy expression, energy eigenvalue expression, as equation number 1. Now once you know the energy of the system, the next step in canonical ensemble treatment is to find out the single particle partition function. So therefore, the single particle partition function, which we are representing as Q1. So Q1 is equal to, remember here it is not a classical system, it's a quantum system where the energies are discrete. Okay, so instead of integration, we will revert back to our older definition of partition function, or the original definition of partition function, that is sum over. Okay, so summation e raised to, right, it was actually sum over r e raised to minus beta er. So instead of r, we have taken here en, because n is a vibrational quantum number. So I can say it is sum over en. Okay, of course, theoretically from 0 to infinity, all possible values, that is our meaning. Okay, e raised to minus beta en. Okay, beta en, right? I'm using the curly letter for e here. Okay, whatever symbol, that doesn't matter, So this is the thing. So now you can just substitute it. So what will be the thing? It is equal to, you can substitute for en from equation number 1. So it becomes sum over n equal to 0 to infinity, right? So e raised to minus beta times En is n plus half h cross omega, right? N plus half h cross omega. So that is the substitution. Now what you can do here, since the summation is running from n, summation is binding on n only, so there is you can split the exponential of the function here as two terms. One term that depends on n and other term which does not depend on n. Okay, so I'm taking the term which is independent of n outside the summation. So what do we think? That will be e raised to minus beta h cross omega by 2. So that term, so beta h cross omega by 2. So these terms put together, okay, I'm taking it outside. So what will be remaining there inside the summation is into sum over n. I'm not writing from 0 to infinity and all, it's understood. So e raised to minus, okay, minus beta h cross omega, that is there, and there be minus beta h cross omega into n will be there, which I'm writing as whole raised to n for some reasons which you will understand. Raised to n, you know, okay, e raised to x raised to n will be raised to nx. So that is the thing. So now what we can do is that we can use series summation equation. Okay, so there is a result that sum over n equal to or something, okay, n equal to 0 to infinity. This is a series summation. Anything raised x raised to n is simplified as 1 divided by 1 minus x. We'll be using this particular simplification in the quantum harmonic or in the quantum statistical mechanics also. So this is a series summation. Sum over n equal to 0 to infinity of x raised to n will be equal to 1 by 1 minus x. So you can here treat e raised to minus beta h cross omega as some x. Okay. And so using this simplification, our expression will become e raised to minus beta h cross omega by 2 into, so I'm using this one, so 1 divided by what should be the thing, 1 minus x is equal to e raised to minus beta h cross omega, 1 minus e raised to minus beta h cross omega. So which yeah, of course, okay, we can write it as such. So it's equal to the same thing, only I'm writing it, I'm beautifying it, that's all. E raised to minus beta h cross omega by 2, of course, divided by, okay, same thing, only I'm writing it, 1 minus e raised to minus beta h cross omega. So let me call this one as the second equation, right? So we got q1. What is q1? Q1 is the single particle partition function. Now you know what's the next step. So you know that in all these systems we are considering the particles are non-interacting with each other. So why do we take that the particles are non-interacting? Okay, so like you have seen in the case of classical ideal gas derivation also, we considered that the particles are non-interacting. So the immediate consequence of this assumption is that you can take the total energy of the system to be just the summation of the energies of individual particles. Okay, നമ്മൾ ഈ പാർട്ടിക്കിൾസിനെ നോൺ ഇൻട്രാക്ടിങ് എന്ന് എടുക്കുന്നതിൻ്റെ എന്താണ് ഏറ്റവും വലിയ നമുക്ക് കിട്ടാൻ പോകുന്ന ബെനിഫിറ്റ് എന്താണെന്ന് പറഞ്ഞാൽ ഇറ്റ്സ് ആക്ച്വലി ആൻ ഐഡിയലൈസേഷൻ. ഇറ്റ്സ് ആക്ച്വലി ജസ്റ്റ് ലൈക്ക് സ്കിപ്പിംഗ് സം മാത്തമാറ്റിക്കൽ ഡിഫിക്കൽട്ടീസ്. നമ്മളിങ്ങനെ എടുക്കുന്ന ഗുണം എന്താ വെച്ചാൽ പാർട്ടിക്കിൾസ് തമ്മിൽ അന്യോന്യം ഇൻട്രാക്ഷൻ ഇല്ല എങ്കിൽ ഓരോ പാർട്ടിക്കിളിൻ്റെയും എനർജി മറ്റൊരു പാർട്ടിക്കിൾ എനർജിയുമായിട്ട് ബന്ധപ്പെട്ടിരിക്കുന്നില്ല. അതിനാൽ നമുക്ക് ഒരു സിസ്റ്റത്തിൻ്റെ പാർട്ടിക്കിൾ സിസ്റ്റത്തിൻ്റെ ടോട്ടൽ എനർജി കണ്ടുപിടിക്കേണ്ട അവസ്ഥ വരുമ്പോൾ എന്ത് ചെയ്താൽ മതിയാവും? ഇൻഡിവിജ്വൽ എനർജീസിനെ സം ചെയ്താൽ മതി, കപ്പിൾഡ് ടേമുകൾ ഉണ്ടാവില്ല. അപ്പോൾ ഇവിടെ ഫസ്റ്റ് പാർട്ടിക്കിളിൻ്റെ എനർജി E1 ആണ്. ഓക്കെ, സെക്കൻഡ് പാർട്ടിക്കിളിൻ്റെ എനർജി E2 ആണെന്ന് എഴുതുക. ഞാൻ ഐ എം നോട്ട് കൺസിഡറിങ് ക്വാണ്ടം സ്റ്റേറ്റ്സ് നൗ. E1 E2 അല്ലെ, ഓക്കെ, ഐ ക്യാൻ റൈറ്റ് ഇറ്റ് ലൈക്ക് ദിസ്. ഫസ്റ്റ് പാർട്ടിക്കിൾ എനർജി E1 ആണ്, സെക്കൻഡ് പാർട്ടിക്കിൾ എനർജി E2 ആണെന്ന് എഴുതുക. അപ്പോൾ ടോട്ടൽ സിസ്റ്റത്തിൻ്റെ എനർജി കണ്ടുപിടിക്കാൻ നിങ്ങൾ ജസ്റ്റ് E1 പ്ലസ് E2 പ്ലസ് E3 എന്ന് നിങ്ങൾ സം ചെയ്താൽ മതിയാവും. ഓക്കെ, അപ്പോൾ പാർട്ടീഷൻ ഫംഗ്ഷൻ കണ്ടുപിടിക്കാൻ, സിസ്റ്റത്തിൻ്റെ n പാർട്ടിക്കൽ പാർട്ടീഷൻ ഫംഗ്ഷൻ കണ്ടുപിടിക്കുക എന്ന് പറയുന്നത് എളുപ്പമായിരിക്കും. എന്തായിരിക്കും n പാർട്ടിക്കൽ പാർട്ടീഷൻ ഫംഗ്ഷൻ എന്ന് പറയുന്നത്? എന്തായിരിക്കണം? തിയററ്റിക്കലി ഇറ്റ് ഷുഡ് ബി ഈക്വൽ ടു സം ഓവർ, ഓക്കെ, ഓൾ ദോസ് തിങ്സ് e raised to minus beta of energy of the total system ആണ് വരുന്നത്. എനർജി ഓഫ് ദ ടോട്ടൽ സിസ്റ്റത്തിന് നമുക്ക് എന്ത് ചെയ്യാൻ പറ്റും? ടോട്ടൽ സിസ്റ്റത്തിൻ്റെ എനർജിയെ E1 പ്ലസ് E2 പ്ലസ് എക്സെട്ര എന്നിങ്ങനെ എഴുതാൻ പറ്റും അല്ലേ? അല്ലെങ്കിൽ അതുകൊണ്ടാണ് നമ്മൾ എന്ത് ചെയ്യുന്നത്, സോ വി ആർ റൈറ്റിംഗ് ഇറ്റ് as വാട്ട് പ്രൊഡക്റ്റ് ആയിട്ട് എക്സ്പോണൻഷ്യൽ ഫംഗ്ഷൻ ആയതുകൊണ്ട് നമുക്ക് ഇതിനെ എന്ത് ചെയ്യാൻ പറ്റും, സോ Q1 ഇൻറ്റു Q2 ഇൻറ്റു Q3 ഇൻറ്റു എന്ന് നമുക്ക് എഴുതാൻ പറ്റും. ബിക്കോസ് ഇ റേസ് ടു ബീറ്റ E1 ഇൻറ്റു ഇ റേസ് ടു ബീറ്റ E2 മൈനസ് ഓഫ് കോഴ്സ് ദാറ്റ് ബി ഈക്വൽ ടു മൈനസ് ഇ റേസ് ടു മൈനസ് ബീറ്റ ഓഫ് E1 പ്ലസ് E2. അപ്പോൾ പ്രൊഡക്റ്റ് ആയിട്ട് എഴുതാൻ പറ്റും. ഇതിൽ Q1 Q2 എല്ലാം ഐഡന്റിക്കൽ ആയതുകൊണ്ട് തന്നെ നമുക്ക് ഫൈനലി എന്ത് ചെയ്യാൻ പറ്റും, Qn ഈസ് ഈക്വൽ ടു Q1 റേസ് ടു n എന്നുള്ള രീതിയിലേക്ക് മാറ്റാൻ പറ്റും. അതുകൊണ്ടാണ് ദാറ്റ് ഈസ് വൈ വി ആർ സ്പെസിഫൈങ് ദാറ്റ് ദ പാർട്ടിക്കിൾസ് ആർ വാട്ട് നോൺ ഇന്ററാക്ടിങ്. സോ ശ്രദ്ധിക്കുക, ഈ ഒരു അസംഷൻ വളരെ വളരെ സിഗ്നിഫിക്കൻ്റ് ആണ് നമ്മുടെ ഡെറിവേഷൻസിൽ. ഓക്കെ, ദാറ്റ്സ് വൈ യു പ്ലീസ് ഡു നോട്ട് മിസ് ഔട്ട് ദാറ്റ് ഇമ്പോർട്ടൻറ്റ് പോയിന്റ്. സോ നൗ let's proceed on. So you got the single particle partition function, therefore the n particle partition function. So therefore the canonical partition function for the n particle system, it's understood, particle system or system of n non-interacting particles, harmonic one-dimensional harmonic oscillator, that will be given by Qn as usual, that is equal to Q1, the single particle partition function raised to n. N is the number of particles in the system. Should we use an n factorial in the denominator here? Think of, should we use an n factor in the denominator here? The answer is a big no. Why? Because of the assumption that we have already made, that we have considered that these quantum harmonic oscillators are localized maybe in their lattice sites. Okay, as we take in the case of crystal structure studies, right? So due to that assumption, we are not dividing by n factorial, because systems which are localized or particles which are localized at their lattice sites can be identified. So they are distinguishable, they are not indistinguishable. So there is no any sort of anomaly or paradox arising out of the indistinguishability. Particles can be distinguished, referring to their lattice sites, right? Using whatever terminologies in solid state mechanics that we are learning, maybe using Bravais lattice, or maybe using what the concept of Miller indices, planes can be identified and the locations also can be identified, right? So that is there. Now just substitute for a thing, so that will be equal to, that's equal to, I can proceed, Q1 I can substitute, that is e raised to minus beta h cross omega by 2 by 1 minus e raised to minus beta h cross omega, that was. So I can put it as e raised to minus beta h cross omega raised to n will become multiplied by n divided by 2 divided by 1 minus, okay, yes, 1 minus, I'm just substituting 1 minus e raised to beta h cross omega raised to n. Yeah, I can just get rid of this particular see, this bracket can be avoided, that's unnecessary, right? Of course. So that's your thing. So I have just substituted Q1 from our previous equation. So this is your equation number 3. Let's see this. Now you know, once you have got Qn, see, can't you see that Qn is a function of n and t? So clearly Qn is a function of nvt, should be, I can say it's a function of nvt, but of course v raised to 0, then it's okay, nvt. So you can see where n is here, where come the t comes, t, because beta is equal to 1 by kt. So from beta, wherever there is a presence of beta in any expression, just identify or sense the presence of temperature there, because that's one reason why beta is regarded as inverse temperature, because of course k is a fundamental constant. So that is Qn. Now you know, once you get Qn for any system in canonical ensemble, the very next step is to calculate the Helmholtz free energy. Therefore the Helmholtz free energy, I'm writing simply as abbreviated HFE, that is A. What is A equal to? I think by the time you should be familiar. A equal to minus kt log Qn, minus kt log of Qn, right? So I can just substitute here, that's equal to Qn. Yeah, you can write Qn. See, if you are not using equation number 3, I can depend upon this expression. Qn can be written as Q1 raised to n, so it will be equal to, I'm just writing, it's equal to minus kt log of q1 raised to n. You can do in any way, so this is all choices. So which can be written as minus nkt, n is taken, log a raised to b, okay, log q1. So we are rewriting it in terms of log q1. Okay, you can do in any way depending on whatever is possible. So minus nkt log q1, that's all same. Now I can substitute, I can use q1 expression, so that is equal to minus nkt into log of q1. What is our q1? Q1 was something except this en value, right? Okay, something except this en value, that will be q1. So it will be equal to log a by b form, right? So it will be log a minus log b. So when you take log of this e raised to minus beta h cross omega by 2, that will be simply that minus beta h cross omega by 2, right? So minus beta h cross omega by 2, then minus log of, right, minus log of that quantity into bracket, that is what, 1 minus e raised to minus beta h cross omega, right, minus beta h cross omega. So let me just proceed on. So what it becomes finally, it's equal to, just you can open the bracket and check it. So what will be that? Remember, here there is a kt outside and here there is a beta. Okay, and you know beta equal to 1 by kt. So that's kt and beta will be getting cancelled away straightforward here. So here minus minus it will become plus. So first term will be n h cross omega by 2. That's a positive term. Then minus minus, once again it becomes plus over here. So that is once again plus nkt, that is the thing, nkt log of that quantity that we have to retain as such, 1 minus e raised to minus beta h cross omega. So that gives you the Helmholtz free energy of the system, right? Now, you know, once you get Helmholtz free energy of the system as a function of nvt, then the remaining steps are standardized. Okay, you take the partial derivative to get other things. So I'm not spending much time on it. I leave it as a assignment for you to take out, but I will give you the equations which you can give a try. So the things are, you can, therefore the pressure, you know what will be the pressure, because the pressure is equal to minus dou A by dou V, and our Helmholtz free energy is not having any dependence on the volume, so the pressure in this case also will be equal to 0 for the reasons that I have already discussed in the previous module. So now the chemical potential, how do you get the chemical potential? Mu can be obtained by the expression dou A by dou En. Okay, and check it whether you are getting. So what will happen that in the previous expression, that n will be getting rid of. So here there is an n, here there is an n, so nowhere else there is n. So only that you get rid of that n from the a expression, you will be getting the expression for the chemical potential, that is h cross omega by 2 plus what, kt log of 1 minus e raised to minus beta h cross omega. That will be giving you the chemical potential. Similarly, what else you can calculate? You can calculate S also. So S is given by minus dou A by dou T. You know, it is with respect to T, V and En. You are getting all those physical quantities. So which just try it out. Take the derivative of A expression with respect to temperature and see whether you are able to finally get this expression Nk times beta h cross omega divided by e raised to beta h cross omega minus 1. You know from where it comes. It comes from logarithm, derivative of the logarithm. It will be a product rule that you will have to use there, because there are two expressions having temperature. So remember, beta has got that temperature. Okay, beta has got the temperature dependence. So any term with beta should be just done with care when you take derivative with respect to temperature. So that is one thing, minus log of 1 minus e. It's a very simple, you see, just steps. You can just try it, give it a try, or if you need any clarity of steps, you can refer back to MCT notes. Okay, that's already done for you to save time. So give it a try. So try it. That's all. Okay, now similarly you can just calculate internal energy U. What is internal energy U equal to? U can be done in any method, A plus Ts or dou by minus dou by dou beta of log Qn, whatever, you can just do that. But A plus Ts will be simple because A is already there, and on substituting you will be getting this one as what? En h cross omega by 2 plus En h cross omega divided by e raised to minus beta h cross omega minus 1. Never try to memorize any of these equations. Just I suggest you to memorize the recipe and be confident in your algebra of taking simple partial derivatives. And similarly, Cp and Cv, you know, both are going to be equal. For this one, Cp Cv is equal to dou u by dou t. In this case, because P is equal to 0. So nk, this is the thing that you are going to get. Give it a try once again. H cross omega by kt or beta h cross omega square into e raised to beta h cross omega by 1 minus, or sorry, e raised to beta h cross omega minus 1 the whole square. So please try these things. Try these things also. So that's about the quantum harmonic oscillator. By that our discussion of two common systems as application of the method of canonical ensemble is concluded. Now we are left out with the consideration of energy fluctuations in canonical ensemble, which I will do as a separate lecture and upload it. Please continue with the discussion. We will try to cover the remaining topics as soon as possible. Thank you.